As we've discussed many times on the show, fleet assets like locomotives, aircraft, and maritime vessels generate massive volumes of data thanks to their copious digital components. Collecting this data allows fleet owners to solve a wide range of problems, from eking out efficiency gains to improving asset maintenance and monitoring for cyber intrusions. Data scientists use myriad techniques to solve these problems, many of which include elements of artificial intelligence, or AI, a field of study which seeks to enable computers to mimic some of the perception, learning, problem-solving, and decision-making of human minds. In this episode, special guests Walter Tackett, Dan Morton, Matt Rogers, and Ellie Daw discuss what AI is and is not, what kinds of fleet inference problems it can help solve, and exciting new trends in this field. Ellie Daw is the product lead of anomaly detection and data science at Shift5. Her focus is aligning analysis with scalability and impact for customer datasets. She comes from a background in applied cryptography, secure protocol design, and industry research for emerging technologies, such as quantum and private computation. Dr. Walter Tackett is a senior data scientist at Shift5. He's an electrical engineer who specializes in signal processing and AI, and whose PhD dissertation focused on genetic programming and neural networks. He's developed large-scale AI applications that include image recognition for autonomous vehicles and natural language bots for customer interaction, as well as anomaly detection and forecasting for investment risk management. Dr. Dan Morton is a data scientist at Shift5. His focus is solving real-world customer problems with data. He earned his PhD in particle physics, searching for rare events in large datasets. Matt Rogers is a security researcher and PhD student at the University of Oxford, working on the cybersecurity of fleet assets. Matt, Dan, Walter, Ellie, welcome to the show.
Thanks for having us.
I'm excited. This is quite a large group, so I'm excited. I'm sure there will be lots of interesting perspectives. So we set the record for planes, trains, and tanks with the size of the panel here. So great. Well, I think maybe we can start off with a little bit of framing here. So what we're going to talk about is fleet data. So data that comes off of fleet assets like locomotives, aircraft, maritime vessels. And this has been a recurring theme in the show. But I think, Ellie, maybe can you start us off by explaining how locomotives, which you think of as these very old, 100-year-old assets, are generating data?
Yeah, so it's interesting. And like you said, I think we don't assume that there's just like a big data science problem in sort of the train world. But if you think about it, all of the components in an engine are actually like digital components, and they have to talk to each other some kind of way. And if you come from the computer science world, like this is analogous to kind of networking, right? Like TCP/IP networks in like normal internet communications. But they are kind of constantly talking to each other. This is how they can decide like, hey, speed up or slow down, or like even the HVAC systems, right? Things like this are all talking to each other on their own internal network. So even though it seems like, oh, those are like really old machines and kind of big systems, how could they be, in the computer science world, they do generate a lot of data. And one of the big problems is like collecting this data because it's not like internet accessible, right?
When these systems were designed, they weren't designed to broadcast data because the quantity of data was far exceeded what anybody could reasonably store, use, or proliferate. So these are systems which while they're still digital, they're very old digital systems. So if you've ever had any incompatibility issues with operating systems or anything like that between something very old or new, then you'd understand that you expect some challenge to exist between dealing with something developed in the 70s and 80s, taking those digital signals and transforming them into something that we use in modern times. So a lot of times it does involve specialty hardware or having special designs to bridge that gap.
Yeah, they're kind of sitting on their own network, right, and talking to each other, and we have to like be able to listen in on that. And I think to Dan's point too, if you think about every little component in a train or in like any other vehicle, doing its normal operation, there's just a lot of talking going on that network. And so that's kind of where the like big data science problem comes in, is after we figure out how to collect it, it's like, okay, all of these components are talking about all of the things that they're doing. And we just have this like data volume problem now, right? And we have to kind of extrapolate what's useful out of that big volume of data.
Yeah. And I mean, I think the other idea here is that OEMs, the manufacturers of these assets, started replacing components bit by bit. And so digital components accreted over time into these systems. And I think we're only now starting to think like, well, hold on a second. Now we've got dozens of these digital components that are communicating over this data bus. If we were to design this from first principles all over again, or think about this thing as a network of computers, because it is, what kinds of possibilities does that open up that we haven't thought of, rather than the very tactical of like, well, engine control is just easier if we do it electronically, or this sensor is more reliable when it's electronic. Now we think about, well, what can we do with the sensor data that isn't just immediate control of the asset? It's like, let's pull this data back and now like try to solve some inference problems. So Matt, what are some of the classes of problems that are addressable with this full take packet capture that you're able to do on these fleet assets?
Yeah, so I mean, the main things are both anomaly detection, from a lot of what I'm interested in from a cybersecurity researcher, and then also trying to do predictive maintenance so that, given all of this data, kind of an interesting tidbit about the design for these systems is that they explicitly say not to communicate any data on these serial data buses across all of these different digital components, unless that that data is useful for the other digital components. And so by definition, all of this data is incredibly valuable for how this system operates over time. And so just by collecting all of it and doing something with it, you might be able to predict both how the system is going to act in the future, or make some assumptions on, well, it's been acting this way in the past, and maybe some attacker came in there and tried to change the behavior of the system. But, well, we can maybe model that and do some fancy stuff in order to predict exactly how the system is meant to be operating.
That makes a lot of sense. And Walter, I know you've done a lot of work in parsing data to try to find out if there are anomalous conditions. And at some level of abstraction, maintenance issues and cybersecurity issues are both anomaly detection exercises, right? What are some of the ways that you can use fleet data to tease out maintenance problems for like preventive maintenance, for example, or to detect active cyber attacks?
Well, I think that, certainly it gets back to the idea of many of these systems were designed in the 70s, and the people who were designing the data buses never really thought about, imagine if all of these trains could be instantaneously connected by a high-speed connection so that somebody in a central location could look at the entire fleet at once and look at all the data coming in. And there's a couple things that I like, guiding principles of large parts of data science, which are that, first of all, much of data science is really just statistics, and that furthermore, data science is really about 95 to 98% data acquisition science and data cleaning science. So many times the problems that we solve are really ones that are applying relatively straightforward statistics to data that is simply hard to get, because we have to put the boxes on there and get it. But once we do, we can certainly say that which of these things is not like the others. That we've got a signal coming off of one train that is very different from the ones that we're getting all the other ones that pass through the same area and location with the same load, et cetera. So in that sense, we can use techniques like correlation and things like principal components, which is and principal components is a classic example of something from statistics and signal processing that is now considered dimensionality reduction in data science. But that's okay. It's good to be able to use techniques that have a long history and are well understood by scientists and engineers in order to apply them. So in short, I think that there's a lot of things that simply can be done once you've gathered all the data, and so from there, inference often consists of really looking at the mass volumes of data and saying, for those trains which failed in some way, but we'll just use trains as an example, and for a particular component that's prone to failure, is there some pattern in the telemetry that it's sending back that was abnormal, that differentiates itself. For example, the dropouts in a pulse train, or other things that might, or lags, or sending different signals. And if we can use methods such as, once again, k-means clustering, a method from statistics that is fairly well known for seeing how signals or patterns of features fall into natural groups without having to tell them how to fall. And if we see that there's a group of things that segment themselves out from the others, so that is, the say failing control units on one train, or failing control units separating themselves out from non-failing control units, then we could simply identify that division and say, well, it seems that there's a naturally occurring phenomenon we see in things that are about to fail, which is different from those that are not about to fail. And so I think that's an example of overall, to get back to the original theme, that we can apply things, like principal components and clustering to data that was very hard to gather and bring together back when the systems were first designed.
Matt, so I know you've done a lot of work in reverse engineering OT assets, things like vehicles, where we don't have very good documentation or sometimes no documentation about what the protocols actually mean on the wire. And so you're left with this practice of sort of manipulating the thing, moving transmissions around, opening windows and door locks, and then observing the traffic that results emanations on the bus. Now, this requires quite a bit of data cleaning, in the sense that you need to enrich the bits and bytes that are on the wire into something that people and algorithms can understand. But it's pretty complicated. And I know you've used a number of techniques that are full-blown inference data science style tools just to get the data tagged and cleaned properly. Can you tell us a little bit about that?
Yeah. So if we go back to what you were referencing, we're getting all this data as ones and zeros on the bus. But back in the day, when people were trying to hack these vehicles or really do anything with it, you go back to 2010, and they're just putting cars up on stilts and just ramming random bits through these wires until a wheel starts turning, a brake is triggering, until you can basically develop enough stuff automatically that you figure out what's going on, right? In traditional networks, this would be fuzzing it. And so, we've elevated ourselves a little bit beyond that. And the reason why we had to do it in the first place is because this data is proprietary. So the people who own it, the original equipment manufacturers, either do not know or are not inclined to provide to everybody the data sheets for how everything works. Some cases, the do not know is a little more terrifying than the other option. But once you get from a consumer automobile, sure, easy enough to put on stilts, fine. What about a truck, or how about a fighter jet? A little harder to just kind of put up and run through the paces and get actual operational data. And so what you have to do is, once you collect those ones and zeros, you have to make some inferences into what it actually means. So there's been a number of ways that people have gone about this. The kind of summary of it is that you can kind of separate data into two different sorts of values. You have scalar values and you have discretes. So you've got these states that the vehicle operates in, and then you've got really common things, like on a vehicle, like in a car, you might expect the speed of the engine to be something that changes pretty dramatically. And so, or, in a sort of consistent manner. So you kind of just try to group all of the bits that you have into sets that you can identify flags and things that actually change, as if it's the RPM of the engine, or some transmission setting or something like that. And you try to group all of these bits and identify them on the fly, and then use that as a classification mechanism for reverse engineering. Or if you're extremely lucky, or some tortured soul, then you are given a PDF, probably a PDF that is composed entirely of images, so that you cannot search through it and instead have to do a lot of manual work. And then you have somebody who tells you what all of the data means, which takes a lot of the guesswork out of it. But you run into another problem here, in that I think anybody who has dealt with any protocol that has ever existed has learned that, yes, the protocol exists, but does every individual manufacturer who has independently implemented that protocol actually follow every bit of it? And the answer is no. And so oftentimes you still have to go through and look at the data and look for those weird values that don't really work. And so a lot of that ends up being a manual process, or baking to whoever gave you the data set to just explain what in the world they were thinking. But it's really a mix of trying to create these inference problems while also, sometimes they just give you all of the information and then you can kind of take the wheel from there.
Yeah. It's complicated. There's a lot of work in what Walter was saying about 90% of data science being cleaning all of this stuff up to the point where you can actually solve the problem for the user is really important and sometimes tedious, but it can be accelerated by smart techniques. Walter, once we get to that 10% where we've got clean data that is the input into this inference engine that we're designing, give us a sense. You talked about some techniques like k-means clustering and component analysis that they've been around a really long time. And, we hear this term artificial intelligence. Like, what does that mean to you? Where does the line start for artificial intelligence versus some of these tried and true techniques? Are they AI, or is there some like new classification that qualifies things as AI? Like, what's your opinion?
Well, I think AI is really, it comes down to being more of a goal or a label than anything else, because what it really means, it plays on our behavioral biases. In other words, when we think of things as being exclusively things that are done by humans and we see machines doing them, then we call that AI. And the first inklings, I think we saw this in modern society, were in the Industrial Revolution, where we hear people talking about a steam-powered brain and things like that. And then when control systems came along in the 40s and 50s, the cybernetics was considered, a form of AI, and so it goes on through rule-based systems. And then as many of these things, such as chess playing, become commonplace, where we just say, well, there's a chess playing computer. We don't call it artificial intelligence anymore. So I think that it's really more of a label, and it's better to drill down on the individual techniques. I think we're entering an interesting new time, when it used to be that things would get called AI until they started working properly, but then if they failed, we would remember the failure as AI. And so there was this sort of negative, because it wasn't that AI didn't succeed, it was that it stopped being called AI once it succeeded. And now I think we're sort of moving beyond that, where things are still being called AI once they've succeeded. That would include, applications of reinforcement learning to, game playing, which is, once again, reinforcement learning is derived from control systems techniques like dynamic programming. So I think that there's most things, I believe, that are AI have their roots in something that's not AI. So that classification has its roots in classical statistics, for example, logistic regression or component regression, curve fitting. I think that many techniques, such as what we call unsupervised learning, like the k-means and principal component analysis or singular value decomposition, belong in applied mathematics and electrical engineering and things like that. And I think it may be that rules-based systems, that inference logic and Bayesian systems are probably the things that are sort of the most of all technologies out there. Really were kind of grew because of interest in AI and are sort of their own thing. And then there are people, well, Jeff Hinton might say that deep learning is its own thing, but my opinion is that deep learning is really engineering. That is, it's where people have taken many of these basic AI concepts, and I also would not diminish those accomplishments, but they really figured out how to take really huge scale networks and make them work, which is non-trivial. But yeah, so I think that it's often made of other things, but not always. And certainly, I know that people like Matt have done a great deal of work in applying rule-based systems and making those work. So.
Yeah. So one thing I think that's also important to draw a comparison to is intelligence as defined biologically. because intelligence, of course, in defining a biological system, is a lot different than artificial intelligence as usually defined by computer scientists formally, or as used when developing a product, like Walter was talking about, industrial systems, which would absolutely not qualify as something you would consider biological intelligence, but is very much hit the range of artificial intelligence, where it's taking the role of an intelligent human in response to its environment. Some of the big differences that we can see right away is, and where some things are going, is intelligence as an emergent phenomenon, which is sort of a new concept. And so even our ideas of what intelligence is itself is also evolving with time as we try to get closer and closer to what we are now. And so one of the new terms you also hear a lot of is, and Walter kind of mentioned it, referenced it a bit, is with machine learning, is machine learning, where we can more clearly define something what learning is, where you progressively find patterns in a system through repetition and reinforcement.
I think one other thing to think that's really important is, and it's what Dan brought up, is that there's, we want to think about adaptation in general, and there's kind of two ways to look at it. For example, if I'm trying to track and prevent an intrusion, I don't necessarily need something that is smart like a person, but is smart like a frog grabbing a fly, or I had Michael Arbib as a professor, so I learned all about frogs. But there's the idea that there's a lot of kinds of what I would call adaptive capabilities that living things have when it comes to just their ability to link action with perception. That you don't really need to be smart. You just need to be really good at pattern recognition and really good at reacting appropriately. And so I think that a lot of times it's not really, well, I guess it is intelligence because it's something that a rock or can't do. But I think that's an important goal. And also in the very large scale, there are some interesting applications we've seen recently in I'm biased towards, I'm not really biased towards genetic algorithms, but I have a background there. It's important to also realize that when it comes to adaptation, and we want to think about biology, that most of what we are is determined by evolution, not by learning. In other words, the difference between somebody with a master's degree and somebody with a PhD is a matter of what they've learned in their neurons. But the difference between a person with a master's degree and a cat or a lizard is due to evolution. The really big changes are due to these sort of random changes over extremely long periods of time, and so that really learning is just a small part of adaptation. And if you want to get philosophical, and I think it touches on something Dan said, is that there's also, we have one example of intelligence, and it's a kind of an interesting philosophical question that what does intelligence look like that's not human intelligence? That could computers develop a type of intelligence that's simply orthogonal to what we think of as intelligence, but is nonetheless intelligent?
Yeah, and I think an interesting thing after hearing Alex's analogy and what Matt, Dan, and Walter are all saying about different applications too is there are a lot of really interesting problems that AI and machine learning can solve, but to their point, every system kind of looks different. And you have to kind of know what techniques you need for each certain problem type so that you can solve the problem efficiently, right? There's not necessarily a one-size-fits-all solution to something. You have to still have your subject matter expertise and kind of go through that thought exercise of identifying the problem and kind of deciding what would be the best way to go about solving it.
Spoken like a true product person.
That's very true. I think because we're at the end of the day that we have to be problem driven, we don't set out saying I've put the old saying that when you have a hammer, everything starts to look like a nail. That
Right.
We need to start from the ground up with, we're trying to do this thing with a bus. We're trying to determine, is it an attack on a signal? Is it an attack on at the code level? And that drives whether we use AI or whether we use simple rules or whether we do something, just a simple algorithm.
Right. Yeah, and it's all driven by the user and what the goal is. What problem are you solving, right? And so you start with, well, we want to try and figure out that a locomotive is going to break down before it actually throws a maintenance fault, or we want to figure out, like, is this locomotive idling on purpose, or was it just left there by accident and we're just wasting a bunch of fuel? Is this sort of aberrant timing on the bus a result of some just sort of unusual condition, or is there an attack going on and someone's flooding the bus with things? All of these are going to require different inputs. They're going to require different inferential techniques, and they may be different from platform to platform, right?
This brings us, I think, back full circle to the end of the question, where we want intelligent solutions on these platforms to these problems. And our goal, and to reach our goal, we might use something like machine learning or something else. But in the end, we're going to have something that responds to what we are engaged with in what somebody would consider an intelligent fashion. So in that way, it can be seen as artificial intelligence as a goal, versus in using different techniques in order to get there.
It's a great point, Dan. And, I think it brings up a whole set of really interesting questions about how you operationalize AI. Walter, what are some of the costs that are associated with bringing AI into an overall system to solve a problem?
Well, I think that's what not to throw it back to you, but I think that really depends on the problem. And I'd go further to say that it's really sort of an operations research question, that you have to say, what's, like, as with anything, any other component you bring into the problem, you have to say, what's the budget that I have to spend on it, and really, how much more performance am I going to get by applying this technology, and how much am I going to pay for that, and what's the return? So what's the cost benefit? And I have to view it that way, like I would anything else. It gets back to that fundamental idea that it's not magical. It's an engineering tool.
Yeah, and to that point, it really depends on the exact solution that you're trying to implement, because and what your end goal is. Because if you're dealing with an attacker who only can attack via circuit mechanism, they can implant something on the bus. The kind of security that you need to implement is only a certain bar. And so, you can build your solution around that. And that might not be a particularly complicated statistical method. Maybe you're doing QSUM analysis or something like that. But if you are then going, okay, well, I need to do predictive maintenance, and I don't need to just know if the engine is breaking down. I need to know if the 100 sensors in this entire train are actually performing at their optimal settings. Well, then you need a lot more data inference, and you're solving a much harder problem. And so you have to incorporate all of those costs as you get into it.
Or if you need 200 to take this 200 sensors and make a prediction because you don't have any direct measurement on the system you're trying to actually solve the problem for.
Yeah, we just add more sensors. It's the solution.
It's the solution to every problem except too many sensors. So, I mean, when we talk about a lot of these techniques, machine learning, a lot of statistical inference problems, oftentimes you have this, what in statistical theory we would call parameter estimation, but I think more broadly in the data science community we call training. You have this training problem, so you start with the inference problem at hand. You identify that there may be a collection of techniques that would be useful at inferring about that problem. But a lot of the solutions in the AI and ML communities require you to train the algorithm, even though you've selected, we're going to use a neural network here, or we're going to just do a simple regression. Walter, tell me a little bit about what that training process looks like. What is it, and how do you go through it? And then maybe follow up with, how do you make sure that it stays up to date as the system might be changing?
Well, I think that, once again, I think that classical statistics has a lot to say about that, and this is where really actually the classical statistics and modern statistics converge. The only difference being that classical statistics uses distributions, assumes what type of distribution you're doing and you're encountering, and maybe machine learning or statistics with computers might just assume an empirical distribution. But you still have to be very careful about the bread and butter of whether, no matter what you call it, is that if you're going to learn from a set of data, you have to separate it into a training set and a test set and an amount that you hold back that you just absolutely never look at until you're completely done. And during this process, you have to ascertain how much of the problem space is being covered. In other words, do you have a representative sample? Which is the same problem that some classic problem in the 1930s with telephone surveys. And it turned out that only a certain demographic had telephones. And so that the election predictions they were trying to make with telephone surveys were off the mark. And that problem still exists today in just as much in anything else. In other words, if we're looking at the bus on some vehicle and saying, well, this is its nominal operation, but we don't really drive it around that much, and we don't really probe all the possible things that could happen with the vehicle, but we say this is a representative sample and we train on it, then either we could miss an obvious attack, or we could set off alerts to things that are actually normal operation, but they're not in the set of data that we gathered. And there's really a question of does my training data span the complete range of inputs I'm likely to see? And with something like the vehicle, I'm not sure that that's a realistic thing to do. And then if it does span, is it also dense enough data? That is, do I have enough points? I defer to Dan because Dan has a lot of experience in this too.
Yeah, so this gets especially complex, especially when we're talking about the vehicles. In the vehicle space, this is very similar to problems where you have a very log scale event expectation. So you could easily expect an event that you care about to occur 1,000 times less frequent than an event than your normal nominal. Okay, what's happening with their vehicle? What message are we seeing? So you get these 1 in 1,000, or sometimes one. For example, in my experiment, going back to my physics situation, it was 1 in 10 to the 8th events we cared about. And then a lot of your backgrounds are occurring on 1 to the 1,000 scales, 1 to the 10,000. So you have to consider both, how are we representing this? How do we have enough to extrapolate or interpolate what's occurring at these different scales, and how do we handle this? It actually becomes a very complex question. And especially when you don't know what's actually going to occur, like vehicles, we don't necessarily know all the boundaries which will occur in good states. So you have to use sometimes you have to rely on intuition when you don't have data. Sometimes you have to rely on estimating and then reevaluating what you're doing a few times. And other times you have to try to generate artificial scenarios where you can get these far edge cases in order to have some characteristics. And then you have to change, as you do your training, you have to build a training schedule which actually considers all of these factors.
I guess this also just double underlines the whole idea that platforms are unique, and that every time you're solving an inference problem for a particular platform, it requires diligent work in determining what the right approach is, and also how do you do data collection, how do you train the algorithm, and makes it even more unlikely that there's a universal approach that's going to solve all of these problems, right?
We would be remiss to also not mention that, if we're popular enough, there's going to be somebody out there watching this podcast trying to infer what algorithms we use to defend the bus, because they're an adversary and they want to they're using this kind of bus and this kind of algorithm, and we know that particular algorithm is susceptible to these problems, and so they're going to design an attack to fool our learning algorithms. And as a matter of fact, adversarial learning is, I think if you follow the science, follow science and technology, that people have done that with road signs for autonomous vehicles, because a lot of times when people train learning systems, that they don't really realize that they haven't covered all the bases, and so that's where you get the piece of tape over the road sign that causes the autonomous car to swerve. So yeah, but that's a thing. So
it sure is.
It's in addition to all the existing problems of training, we work in a very adversarial environment, and so we have to cover our bases in multiple redundant ways.
And I think Walter had kind of mentioned this before too, but like the quality of the data that you're feeding into this is going to affect like the quality of your model and how well your AI actually performs. And I was thinking, like, Walter was kind of talking about trying to evade different like classifications, but there's also the problem of data poisoning, right? Like if you don't have a representative set, or if an adversary can like inject false data into the training set, that can have big repercussions on, whatever ends up getting deployed.
Garbage in, garbage out. Very often heard phrase in any shop.
That's when Microsoft put up a chat bot, that could learn from its interactions with people, and they turned off that learning capability really quick.
It's not a nice reflection on the state of humanity, or at least Twitter, which we can have an argument about whether that's a representative sample or not.
That's definitely its own unique set.
Yeah, I think within 18 hours, it was like violating Twitter's terms of use, because it was like spouting conspiracy theories and other like unsavory things.
To jump on that, there's there are these unsupervised models that you don't give them any training, but particularly with these vehicle scenarios, you have to be really careful when you're considering these unsupervised models, because given a huge data set, you can try to identify anomalous behavior, but to go back to sort of Ellie's point of the adversarial nature, if an attacker is already on the system and you're trying to do an unsupervised model and just trying to figure out what's anomalous based off an attacker that's already there, there's a lot of room for basically them adversarially getting around your system. And so a training model helps prevent that and makes it so that you can be a bit more confident. But for maybe like a predictive maintenance setting or something like that, maybe a bit more safe to do something like an unsupervised model.
Yeah, it makes a lot of sense. And I guess in the time that we have remaining, we've talked a lot about machine learning, AI, and inference tools that exist or have existed, for the past 100 years. Walter, what are some of the exciting directions for AI, and how do they relate to the problem of operating fleets?
Well, I think the thing that I've done some hands-on work with that I think has a lot of promise is explanatory AI. That trying to generate explanations from AI has been around for a long time. There are some techniques out there, particularly what's called SHAP, named after a guy named Shapley, who won the Nobel Prize in Economics for cooperative game theory. Is a bolt-on method. You can actually bolt it onto the back end of any learning algorithm you use, and it will use some linear models to come up with some explanations. That being said, it can also be gamed, so it can come up with bogus explanations. But overall, I think that's good, especially for the field we're in, where when an anomaly happens, we kind of have a fighting chance of being able to come up with an automated explanation of what the nature of the anomaly is. So that I think is a very promising thing. And there are others, but that's probably at the top of my list.
Really exciting. Well, I know we're at the top of the hour here, so I just want to say thank you to everyone for joining the podcast. I think this was really successful. This is obviously a huge field, and I'm really excited for us to maybe do another show and get more into the weeds on some of the specifics of different kinds of techniques at some point. I think it'd be really interesting. So Ellie, Matt, Dan, Walter, thank you so much for coming on the show, and hope to have you on again soon. Thank you for listening to this episode of Planes, Trains, and Tanks. If you enjoyed this episode, please consider leaving us a review. To learn more about Shift5 and our products, visit our website at shift5.io or follow us on LinkedIn and Twitter.